A perfect spiral galaxy hangs in the void, obeying every rule we wrote for it. But what if the true story of the cosmos is written by its rule breakers? We are about to embark on a journey to the farthest edges of our understanding, to explore 25 cosmic structures so bizarre they defy our current laws of physics. By the end, you will witness the evidence that our universe might be far stranger and more magnificent than any model predicted. We will confront a wall of galaxies so large it should not exist, and a mysterious flow pulling entire clusters toward nothing. What is the one cosmic mystery you hope has an explanation? Our journey begins with a discovery so immense it redefined the word colossal. Stretching across the northern sky, from the constellation of Hercules to the crown of Borealis, lies a structure that should not be. Astronomers call it the Hercules Corona Borealis Great Wall, and it is the single largest thing we have ever identified in all of creation. To call it a wall is almost an understatement. This is not a solid barrier but a vast thread-like filament, a cosmic riverbank where galaxies gather in numbers beyond counting. Its scale is almost impossible to grasp. It spans approximately 10 billion light-years from one end to the other. Consider that our entire Milky Way galaxy is a mere 100,000 light-years wide. This single structure is 100,000 times larger than our home galaxy. It contains billions of galaxies, each with hundreds of billions of stars. The sheer mass concentrated in this one ribbon of space is staggering, and that is precisely the problem. Its existence is a direct challenge to one of cosmology's most fundamental ideas, the cosmological principle. This principle is a simple, elegant assumption that on the very largest scales, the universe is smooth and uniform. Look far enough in any direction, the theory states, and you should see roughly the same distribution of matter. It is the idea that there is no special place, no central point, and no single structure that dominates the cosmic landscape. The Hercules Corona Borealis Great Wall screams that this might not be true. A structure of this size, forming in the relatively early universe, should not have had enough time for gravity to pull so much matter together across such an unimaginable distance. Its very presence suggests that the universe might be lumpier, more textured, and less uniform than our best models predicted. When it was confirmed, this discovery sparked a firestorm of debate among cosmologists. Some questioned the methods, searching for any statistical fluke that could explain such a concentration. Others saw it as a glorious anomaly, a sign that our understanding of structure formation in the infant universe was incomplete. If this wall is real, what other titanic architectures are waiting to be found, hidden in the deep field surveys of our telescopes? The Great Wall did not just add a new entry to a catalogue of cosmic wonders. It placed a fundamental question mark over one of the pillars of modern cosmology, forcing us to wonder if the universe's largest blueprints are far more complex and dramatic than we ever dared to imagine. That wall of galaxies is an unimaginable concentration of matter, but the universe holds an equal terror in its opposite. In the constellation of Bootes, the herdsman, lies a region of space so profoundly empty it has earned the chilling nickname, the Great Nothing. This is the Bootes Void, a spherical region of near-perfect desolation stretching approximately 330 million light-years across. To put that into perspective, if you placed our Milky Way galaxy at the center of this void, you would have to travel for 150 million years at the speed of light in any direction before you would even begin to see the faint glow of another galaxy. In a cosmos we believe is filled with a web of galaxies, this is a whole of staggering proportions. Statistically, a region this large should contain around 10,000 galaxies. Instead, astronomers have found only a few dozen, scattered like lonely islands in an endless, dark ocean. This scarcity is what makes the void so deeply puzzling. How can a volume of space so vast remain so empty? One leading theory suggests it is not a single void, but a bubble, the result of many smaller voids merging together over billions of years, like soap bubbles combining into one enormous cavity. Another, more speculative idea reaches back to the universe's first moments, suggesting a rare anomaly during the period of cosmic inflation, a tiny patch of space that expanded far faster than its surroundings, leaving behind a permanent desert. The Boots void forces us to confront an uncomfortable truth. Our models of the universe predict a certain level of uniformity, a cosmic foam with bubbles and filaments. But a bubble this large pushes the limits of what those models can comfortably explain. It is a reminder that emptiness on a cosmic scale can be just as shocking and mysterious as the most dazzling structures. While the Boots void presents a terrifying emptiness, another cosmic structure offers a vision of impossible perfection. Drifting in the constellation of serpents, the snake, lies Hoag's object, a galaxy that looks less like a natural formation and more like a piece of celestial jewelry. At its heart is a dense, golden yellow sphere of ancient stars glowing softly like a cosmic ember. Encircling it, separated by a wide, dark gap of seemingly empty space, is a perfect, flawless ring of brilliant blue stars, young and fiercely luminous. This is not a fuzzy spiral or an elliptical blob. It is a near-symmetrical bullseye hanging against the velvet black of space. The contrast is breathtaking, a snapshot of stellar generations frozen in a perfect circle. The immediate, obvious question is how such a serene and isolated structure could possibly form. Our standard explanation for ring galaxies involves a violent, head-on collision. Imagine a smaller galaxy piercing the heart of a larger disk galaxy, like a stone tossed through a pond. The gravitational shockwave sends stars rippling outward in a ring while the central core collapses back. This creates a temporary ring structure, often messy and asymmetrical, but Hoag's object shows no signs of such a catastrophic past. There is no remnant of a galaxy that could have been the bullet, no trail of stellar debris, no distortion in its perfect form. It floats in splendid isolation, a puzzle of peaceful origins. Astronomers are left with only hypotheses, each as intriguing as the object itself. One idea suggests a slow, gravitational instability that occurred billions of years ago within a single galaxy, causing its outer regions to slowly separate and form a distinct ring. Another, more exotic theory proposes it is the result of an ancient galactic merger, so perfectly aligned and complete that it left behind this pristine, circular artifact. The dark gap between the core and the ring only deepens the mystery, a moat of quiet space where few stars dare to dwell. Hoag's object stands as a quiet rebuke to our chaotic models of cosmic evolution. In a universe built on collisions and chaos, it is a monument to an unexplained order, a single, perfect question mark written in starlight. Perfect symmetry is a rare treasure in the cosmos, but sheer scale is its own kind of marvel. Before the Hercules Corona Borealis Great Wall claimed its title, another structure held the record, redefining our sense of cosmic architecture. This is the Sloan Great Wall, a filament of superclusters so vast it stretches for approximately 1.37 billion light-years. To visualize that distance, picture a beam of light, the fastest thing in the universe, setting out on a journey when the first complex life was just beginning to stir in Earth's oceans. By the time it finished crossing this single wall of galaxies, humanity would have evolved, built civilizations, and looked up to discover the wall itself. Its discovery in 2003 was a seismic event in cosmology, assembled from the painstaking data of the Sloan Digital Sky Survey. Here was a structure that seemed to brush against the theoretical maximum size for anything in the universe. According to the standard model of cosmic evolution, there is a scale beyond which the universe should appear smooth, a limit imposed by the age of the universe and the speed at which gravity can work. The Sloan Great Wall did not just approach that limit, it seemed to step right up to the edge and peer over. it forced scientists to ask a fundamental question. Is this wall a statistical fluke, a chance alignment of galaxy clusters that only looks like a connected filament from our vantage point? Or is it a genuine physical structure, a backbone of the cosmic web that grew to an unexpected size? This tension between what we observe and what our models predict is the very engine of discovery. The Sloan Wall's record was eventually surpassed by the even larger Hercules corona Borealis structure, but its legacy is profound. It proved that these titanic filaments were not mere curiosities, but common features of our universe, each discovery pushing the theoretical size limit further into unknown territory. The quest now is to understand what that ultimate limit truly is. Is there a point where no larger structure can possibly form, or will our telescopes continue to find ever greater walls, forcing us to rewrite the rules of cosmic evolution once more? The discovery of ever larger walls seemed to push our models to a breaking point, but the universe had a new shape in mind, one that defied even our geometric expectations. In 2021, astronomers analyzing light from distant quasars stumbled upon a pattern in the data that should not have been there. They found a vast, crescent-shaped alignment of galaxies, galaxy clusters, and intergalactic gas, a structure now known as the Giant Arc. This is not a wall or a filament, but a graceful curve spanning an almost incomprehensible 3.3 billion light-years across the sky, and it lies a staggering 9.2 billion light-years away from us. We are seeing it as it was when the universe was only about half its current age. The scale is once again the central mystery. This arc is so enormous that it covers approximately 1/15 of the observable universe's radius. If you could see it with your naked eye, it would appear larger than 20 full moons lined up in the night sky. Its existence, much like the Great Walls, directly challenges the theoretical limit for how large a single, coherent structure can grow under the standard model of cosmology. That model, built on our understanding of gravity, dark matter, and the universe's expansion, predicts a kind of smoothness on the very largest scales. Structures bigger than about 1.2 billion light-years should not have had time to form through the slow, gravitational clumping of matter. The Giant Arc is nearly 3 times that theoretical size limit. The statistical analysis makes this finding even more compelling. The chance that this specific, curved alignment of galaxies and gas is a random fluke, a simple trick of perspective, is estimated to be vanishingly small, well below 0.0003%. This forces a profound and exciting dilemma upon cosmologists. Either we have witnessed an astronomically unlikely coincidence, a one-in-a-million cosmic illusion, or our foundational understanding of the universe is missing a crucial piece. Some researchers are beginning to whisper about the potential need for new physics, perhaps a modification to our theory of gravity on the largest scales, or a more complex role for the mysterious dark energy that drives cosmic expansion. The Giant Arc is more than just another record holder. It is a question written across the heavens in the shape of a curve, asking us if the universe's blueprint uses a geometry we have not yet learned to read. A perfect curve challenges our geometry, but what if the entire cosmic web is being pulled in one direction? This brings us to one of the most controversial and mind-bending mysteries in modern cosmology, the phenomenon known as the dark flow. Imagine the aftermath of the Big Bang, a searing, uniform flash of light that still permeates all of space as the faint cosmic microwave background. This ancient afterglow is our most important map of the infant universe, and it should be almost perfectly smooth. Yet, when scientists studied the subtle temperature variations in this background radiation, they noticed something profoundly strange. Hundreds of massive galaxy clusters, each containing thousands of galaxies, appeared to be streaming at incredible speeds toward a single patch of sky between the constellations of Centaurus and Vela. This was not the general expansion of the universe which pulls galaxies apart, but a coordinated drift, as if these titanic structures were caught in a cosmic river current flowing towards something we cannot see. The velocities were staggering, millions of miles per hour, and the coherence across billions of light-years defied all conventional explanation. The gravitational pull of every known galaxy and cluster in our observable universe could not account for this motion. The implication was as terrifying as it was thrilling. Something with unimaginable mass, lying far beyond the edge of everything we can observe, was exerting a gravitational tug on our entire local cosmos. This idea ignited a firestorm of debate. Skeptics argued the data was a statistical fluke or an artifact of incomplete measurements. Proponents, however, saw a revolutionary possibility. If the dark flow is real, it could be evidence for something existing outside our cosmic bubble. One radical theory suggests the gravitational influence of another universe, a separate space-time realm born from the same eternal inflation that created our own, is pulling on us from the great beyond. Another idea reaches even further back, proposing that the flow is a remnant imprint from the epoch before our Big Bang, a fossilized directionality from the birth of reality itself. The controversy remains unresolved, with later studies both supporting and contradicting the initial findings. Yet the mere possibility of the dark flow forces a humbling thought. We have always assumed our observable universe is the entire stage, but what if it is merely one room in an infinite mansion, and we are feeling the draft from a door we have not yet found? The possibility of an unseen pull from beyond our universe is a staggering thought, but sometimes the cosmos leaves a mark that is not a pull but a chill. Embedded within the faint, uniform glow of the cosmic microwave background, the ancient afterglow of the Big Bang itself, lies a profound anomaly known simply as the cold spot. This is not a small imperfection. It is a vast circular region of space, nearly 1.8 billion light-years across, where the temperature of that primordial radiation is significantly colder than the surrounding average. Think of the cosmic microwave background as a snapshot of the infant universe, a baby picture showing the first light to travel freely. It should be a nearly smooth tapestry of temperature with only tiny, random fluctuations. The cold spot is not tiny. It is a colossal, freezing blemish on that tapestry, and its existence has sparked a decades-long detective story with 3 primary suspects. The first and most conservative explanation is that it is simply a cosmic coincidence, a statistical fluke in the data so rare it just happens to look like a significant structure. Given the immense size of the sky we survey, one would expect a few unusual patches by pure chance, but detailed calculations suggest the odds of a cold region this large and this extreme appearing randomly are less than 2%. For many scientists, that is too unlikely to accept as a mere fluke, pushing them to look for a physical cause. The second suspect is a phenomenon known as a cosmic texture. This idea stems from theories of the universe's first moments, suggesting that as the fabric of space-time cooled and expanded from the Big Bang, it might have developed defects much like cracks forming in ice as it freezes. A cosmic texture would be a specific type of topological knot in the very structure of reality. If such a texture existed within the volume of the cold spot, its unique gravitational field could have subtly shifted the energy of light passing through it over billions of years, making that region appear colder to us. It would be a fossil, a frozen flaw in the cosmos from its very first second of existence. The third and most dramatic suspect involves a collision with another universe. This theory ties into the concept of eternal inflation, which suggests our universe is one bubble in a vast, frothing multiverse. If another bubble universe collided with ours during the inflationary period, the immense energy of that collision could have left a permanent imprint on our cosmic microwave background, a kind of cosmic bruise appearing as a cold spot. This idea is incredibly speculative, but it represents the kind of radical thinking the cold spot demands. There is a fourth, more mundane possibility that has been investigated thoroughly, the supervoid theory. Could the cold spot simply be caused by an enormous void in the distribution of galaxies, a vast empty region like the Boots void but on a grander scale? Light traveling through such a void would lose a small amount of energy climbing out of its gravitational well, an effect known as the integrated Sachs-Wolf effect, creating a slight cold spot. Astronomers have indeed found a large underdense region of galaxies aligned with the cold spot, but here is the crucial twist: the math does not add up. The observed supervoid is not nearly large enough or empty enough to account for the extreme temperature drop we see. The void exists, but it is like finding a small hill when your data predicts a mountain. It explains only a fraction of the chilling effect. This mismatch is what keeps the mystery alive, forcing us to consider that the true cause might be something far stranger than mere emptiness. The cold spot remains one of the most tantalizing unsolved puzzles in cosmology, a chill on the face of creation that whispers of defects in space-time, or perhaps the shadow of a neighbor we can never see. Our own cosmic neighborhood holds a startling secret, one that could rewrite our place in the universe. While we gaze out at immense walls and vast voids, it turns out we ourselves may be living inside one. This is the KBC void, named for the astronomers who identified it, and it is our home address on a grand scale. Our Milky Way galaxy, along with our entire local group of galaxies, resides not in an average region of space, but within a relative underdensity, a bubble of diminished matter roughly 2 billion light-years across. Picture a sprawling cosmic metropolis, but instead of being in the dense downtown, we are out in the quieter suburbs where the galactic houses are more spread out. This local bubble is not as empty as the terrifying Boots void, but it is significantly less crowded with galaxies and galaxy clusters than the theoretical average for the universe. For decades, cosmologists have operated under the assumption that we live in a typical region, a principle crucial for making sense of all our observations. The potential discovery of the KBC void directly challenges that foundational idea. It suggests our viewpoint is special, not in a central way, but in a sparse one. This realization carries profound implications, particularly for one of the most heated debates in modern cosmology, the Hubble tension. The Hubble constant is the number that describes how fast the universe is expanding right now. We have two primary ways to measure it. The first method looks at the early universe, using the cosmic microwave background as a fossilized record to predict what the expansion rate should be today. The second method measures it directly by observing the distances and speeds of nearby stars and galaxies, like reading mile markers on a cosmic freeway. The problem is these two methods stubbornly disagree by a significant margin. The local measurements give a faster expansion rate than the predictions from the early universe. This discrepancy has caused a crisis, with scientists questioning everything from the nature of dark energy to the possibility of new, unknown particles. The KBC void offers a fascinating and elegant potential solution. If we truly are living inside a giant cosmic bubble, it changes our local perspective in a critical way. Gravity from all the mass outside our void would be pulling on the galaxies inside it, subtly affecting their motions. More importantly, the relative emptiness of our region means the local expansion of space itself might be slightly faster here than in the denser, average universe. Our direct measurements would therefore be recording this locally boosted expansion rate, while the early universe method predicts the global average rate. In essence, the Hubble tension might not be a sign of new physics, but a sign that we have been reading the cosmic map from an unusual location. The debate is far from settled, but the KBC void hypothesis transforms a potential flaw in our models into a thrilling feature of our reality. It suggests that to truly understand the cosmos, we must first understand the unique window from which we are looking out. Our place in a cosmic void reshapes how we see expansion, but it also begs a deeper question. Where exactly is home on the grandest map of all? For most of human history, we believed our Milky Way was the entire universe. Then we learned it was just one galaxy among countless others in a local group. That group was part of the Virgo supercluster, a sprawling collection of galaxy groups centered on the massive Virgo cluster. That seemed to be our final cosmic address until a revolutionary new way of mapping the heavens revealed we were thinking about it all wrong. The old maps were based on simple proximity, drawing boundaries around galaxies that appeared close together in the sky. But in the accelerating universe, proximity can be an illusion. Two galaxies might appear side by side from our vantage point, yet be flowing in completely different directions on the cosmic river. A team of astronomers led by R. Brent Tully set out to chart these rivers by meticulously measuring the velocities of tens of thousands of galaxies. Subtracting the uniform expansion of the universe, they could see the underlying currents of gravity, the secret motions that revealed true allegiance. What they uncovered was a structure of breathtaking scale and beauty, which they named Laniakea, Hawaiian for immense heaven. Laniakea is our home supercluster, a vast gravitational continent containing approximately 100,000 galaxies, including our own Milky Way. It stretches over 500 million light-years. Picture a colossal cosmic watershed. At the heart of Laniakea lies a gravitational anchor so powerful it dominates the motion of every galaxy for hundreds of millions of light-years around it. This is the Great Attractor, a mysterious region of immense mass hidden behind the dust of our own galaxy's central plane. Every galaxy within Laniakea, including ours, is flowing inexorably toward this central gravitational valley. The boundaries of Laniakea are not drawn by arbitrary lines in space, but by the crests of these gravitational basins. They are the continental divides of the cosmos. On one side, galaxies flow toward the Great Attractor and belong to Laniakea. On the other side, they flow toward a different dominant center, like the neighboring Perseus-Pisces supercluster. This redefinition was a profound shift in perspective. Our Milky Way is not merely in the Virgo supercluster, we learned. The Virgo cluster itself is just one major knot within the far greater expanse of Laniakea, and we reside not at its center, but on a distant suburban filament, a quiet tributary streaming toward the Great Attractor. We are not at the center of anything. We are residents of the gravitational countryside, living on the outskirts of a metropolis of 100,000 galaxies, all caught in the same slow, majestic river of gravity. Laniakea taught us that to understand our place, we must look not just at where galaxies are, but where they are going. The heart of our immense home, Laniakea, is not a brilliant city of light, but a shadowy enigma. This is the Great Attractor, a gravitational anomaly of such profound power it bends the paths of our entire galaxy and 100,000 others. For decades, it was the universe's greatest unsolved mystery, a hidden force we could feel but not see. The problem was one of cosmic geography. The Great Attractor lies in the direction of the constellation Centaurus, a region of the sky that happens to be directly behind the dense, dusty central bulge of our own Milky Way. Astronomers call this the zone of avoidance, a frustrating band where the thick fog of interstellar dust and stars blocks our optical view of the distant universe beyond. It was like trying to identify a distant mountain range while standing in the middle of a blinding sandstorm. We knew something was there because of its immense gravitational pull. By measuring the peculiar velocities of galaxies, scientists could see our local group and the entire Virgo supercluster were not just expanding with the universe. We were being dragged sideways at over 1 million miles per hour toward this unseen point. The sheer amount of mass required to cause this motion was staggering, equivalent to tens of thousands of Milky Way galaxies, all concentrated in a region we could not directly observe. The mystery began to unravel with new eyes, telescopes that could see not in visible light, but in wavelengths that pierced the galactic dust. X-ray and radio observations finally peered through the zone of avoidance, revealing a crowded and violent metropolis. At the core of the Great Attractor lies the Norma Cluster, a massive gathering of galaxies so dense and hot it glows fiercely in X-rays. This cluster is a major component, a significant knot of mass that accounts for a large part of the gravitational pull. But here is the crucial twist: the plot thickens. Even when we add up the mass of the Norma Cluster and all the other galaxies now visible in that region, there seems to be a shortfall. The gravitational tug we feel is stronger than what the visible matter can explain. This suggests the Great Attractor is not a single destination, but perhaps just the nearest dip in a much larger gravitational landscape. Our motion may be part of an even grander flow, pulling us toward something far more immense lying even deeper in the shadows. The Great Attractor, once a singular mystery, has become a doorway, a signpost pointing toward structures of such scale they still elude our full comprehension. The Great Attractor pulls us in, but it is only half the story of our motion. For every gravitational valley in the cosmos, there must be a corresponding peak. This brings us to a structure that is defined not by what it is, but by what it is not: the Dipole Repeller. If the Great Attractor is a cosmic sinkhole drawing matter inward, the Dipole Repeller is the vast, sloping plane we are sliding away from. Located in the opposite direction of the sky from the attractor, this is an immense region of extraordinary emptiness, a void so profound its lack of gravity acts as a repulsive force. Think of it like this: gravity is not just a pull from massive objects, it is also a relative push from areas with less mass. Imagine you are on a hillside covered in snow. You will naturally slide down into the valley because the ground slopes away from the peak. The Dipole Repeller is that cosmic peak, a region of such low density that the surrounding, denser universe effectively pushes us away from it, toward the gravitational well of the Great Attractor. Our local group's journey through space is not a simple free fall toward a single point, but a balanced drift between these two titanic influences, one pulling, the other pushing. This realization transforms our understanding of cosmic voids. They are not merely passive, empty spaces between the glittering filaments of the cosmic web. They are active, dynamic players in shaping the large-scale flows of the universe. Their absence of mass creates a kind of negative topography, a gravitational landscape that guides the motion of galaxies as surely as mountains guide rivers on Earth. The Dipole Repeller, spanning hundreds of millions of light years, is one of the most significant of these empty actors. Its existence, inferred from the precise mapping of galaxy motions, solves a key piece of the puzzle surrounding our local flow. The pull of the attractor alone could not fully account for the speed and direction of our motion, but when combined with the push from the repeller, the model fits beautifully. This teaches us a profound lesson about the cosmos. Sometimes the most powerful forces are not concentrations, but absences, and to understand where we are going, we must also map the great expanses of nothing we are leaving behind. Gravity sculpts the cosmic landscape, but some of its most dramatic creations are written in invisible ink. Far beyond the visible stars and swirling dust of a typical galaxy, there exists a ghostly architecture, a structure so vast it can only be seen with radio eyes. This is the realm of the giant radio galaxy, and its newest champion is a leviathan named Alcyoneus. Discovered in 2022, this cosmic monster holds a record that defies belief. Stretching from one end to the other, its twin lobes of radio emission span an almost incomprehensible 16 million light-years. To grasp that scale, if you could place our entire local group of galaxies, including the Milky Way and Andromeda, within one of its lobes, it would be a mere speck swallowed by the immensity. These lobes are not made of stars, they are colossal balloons of magnetized plasma, superheated gas blasted into intergalactic space at nearly the speed of light. Their source is the supermassive black hole at the galaxy's heart. As matter spirals into this gravitational abyss, unimaginable energies are released. channeled into two opposing, pencil-thin jets that shoot out for hundreds of thousands of light years. Where these jets finally slam into the thin gas that permeates the space between galaxies, they inflate these enormous bubble-like lobes which glow brightly in radio waves. What makes Alcyonius a profound mystery is not just its size but its context. The host galaxy at its center is surprisingly ordinary, a sleepy elliptical galaxy with relatively modest stellar mass and a black hole that is not particularly active by cosmic standards. According to our models of active galactic nuclei, or a GN feedback, the most enormous radio lobes should be powered by the most voracious black holes in the most massive galaxies, feasting on tremendous amounts of material. Alcyonius breaks that rule. Its central engine appears underpowered for the monumental structure it has created. This forces astronomers to reconsider the entire environment in which this giant lives. Perhaps the intergalactic medium around Alcyonius is exceptionally thin and uniform, offering little resistance to the jets, allowing them to propagate farther and inflate larger lobes with less energy. Or maybe the black hole's activity has been incredibly stable and long-lived, a slow, steady push over billions of years that gradually built up this titanic structure. Alcyonius stands as a silent giant, its impossible size challenging our understanding of how black holes interact with and shape the universe on the very largest scales, proving that sometimes the quietest centers can create the loudest echoes in the void. The universe's quiet giants can shape space for millions of light years, but some cosmic structures are defined by a spectacular and violent intensity. In the constellation of Phoenix, a galaxy cluster exists that is breaking all the rules of cosmic evolution. This is the Phoenix cluster, a gathering of thousands of galaxies so massive it bends the fabric of space-time around it. At its heart lies a monster, a central galaxy that is not just a quiet retirement home for old stars, as we see in most clusters. Instead, it is a stellar nursery operating at a frenzied, almost impossible pace, birthing new stars at a rate of roughly 700 per year. To put that into perspective, our own Milky Way galaxy creates maybe 1 or 2 new stars annually. This central galaxy is in the midst of a star-forming frenzy, and its existence directly contradicts one of astronomy's fundamental beliefs about how the universe works. For years, astronomers have observed a clear pattern in the most massive galaxy clusters. At their centers, you typically find a giant elliptical galaxy, often the largest galaxy in the universe, filled with ancient red stars and little to no gas to form new ones. These are called cool core clusters because the dense gas at their center should, in theory, be cool enough to collapse and form stars, yet star formation is mysteriously suppressed. The culprit was always thought to be the supermassive black hole lurking in that central galaxy. As gas falls toward the black hole, it gets heated to millions of degrees and is often blasted back out in powerful jets, a process known as feedback. This energetic feedback was believed to reheat the cool gas, preventing it from ever cooling down enough to form stars. It was a beautiful, self-regulating model, black holes acting as cosmic thermostats to keep their host galaxies quiet and dead. The Phoenix cluster shatters that model entirely. Here, in one of the most massive clusters we know, the central black hole is not suppressing star formation, it appears to be fueling it. Observations reveal a complex and chaotic dance. Yes, the black hole is active, pumping tremendous energy into its surroundings, but instead of simply heating all the gas into oblivion, that energy seems to be stirring the pot in a very specific way. Imagine a pot of soup on a stove. If you blast the heat, the soup boils violently and evaporates. But if you carefully regulate the heat and stir it, you can create currents that bring ingredients together. The feedback from the Phoenix cluster's black hole might be acting more like a careful stir than a furious blast. It is creating shocks and turbulence that actually cause pockets of the super-hot, million-degree gas to radiate away their energy, cool down rapidly, and condense into dense, cold clouds. These clouds then rain down onto the central galaxy in a spectacular cosmic downpour, providing the perfect fuel for a stellar baby boom. This discovery turns the standard narrative of black hole galaxy co-evolution on its head. We thought the relationship was one of suppression, a balance where the black hole's fury kept the galaxy in check. The Phoenix cluster suggests the relationship can be one of chaotic creation. The black hole's immense energy can, under the right conditions, trigger the very process it was supposed to prevent. It forces us to ask, is the Phoenix cluster a rare cosmic anomaly, a temporary state in a cluster's life, or is it showing us a previously hidden pathway of galactic growth? This extreme environment is a laboratory for the most violent astrophysics, proving that even our best models must leave room for the universe's capacity for spectacular and rule-breaking surprise. The Phoenix cluster shows us creation born from chaos, but the universe can forge structures of such raw, gravitational might they seem to bend time itself. 7 billion light-years away, when the cosmos was barely half its current age, two galaxy clusters engaged in a collision of apocalyptic scale. This is the El Gordo galaxy cluster, Spanish for the fat one, and it is a title well earned. With a total mass estimated at 3 quadrillion times that of our Sun, it is the most massive cluster known in the distant universe, a titan caught in the act of a spectacular merger. What we witness is not a serene gathering, but a cosmic train wreck in slow motion. Two distinct clouds of hot gas, each representing the heart of a former cluster, have already slammed into one another. The collision was so violent it created a visible shockwave, a searingly hot boundary where the gases meet, similar to the famous bullet cluster but on an even grander scale. This shockwave is a crucial clue, a cosmic fingerprint that allows astronomers to reconstruct the collision's geometry and speed, confirming that we are seeing a genuine, high-energy merger of two already massive structures. The existence of El Gordo at such a young cosmic age presents a profound challenge to our standard model of cosmology, known as lambda CDM. This model, which incorporates dark energy and cold dark matter, makes specific predictions about how quickly structure should form in the universe. Gravity needs time to pull matter together from the smooth soup of the early cosmos. For a cluster of this staggering mass to have already assembled by the time the universe was just about 6.5 billion years old, it implies that the seeds of these structures must have been planted earlier and grown faster than the model comfortably allows. It is as if we found a 1,000-year-old tree in a forest we know is only 500 years old. The timeline simply does not fit. Astronomers are faced with two equally radical possibilities. First, our measurements of El Gordo's mass or distance could be off, though multiple independent studies have converged on its immense scale. Second, and far more intriguing, is the possibility that our standard model is incomplete. Perhaps dark matter interacts with itself in ways we have not accounted for, clumping together more efficiently in the early universe. Or maybe the initial conditions from the Big Bang were not as uniform as we think, with rare, ultra-dense regions that gave clusters like El Gordo a colossal head start. This distant, colliding giant is more than a record holder. It is a stopwatch, and its hands are pointing to a time when the universe may have built its greatest structures far faster than we ever believed possible. These colliding titans reveal the raw power of gravity and dark matter, but sometimes the most profound mysteries are found in the universe's quietest places. Drifting through the Coma cluster, a dense gathering of galaxies 280 million light-years away, is a ghost. Its name is Dragonfly 44, and it is a galaxy that should not exist. Seen through a telescope, it is a vast, diffuse smudge of light, so faint and wispy it was only discovered in 2015 using a specially designed array of telephoto lenses. It contains about as many stars as a typical dwarf galaxy, a mere 1% of the Milky Way's stellar population. Yet when astronomers measured the motions of its stars and its surrounding globular clusters, they received a staggering shock. Those stars were whizzing around at speeds that defied all logic based on the visible matter alone. The only explanation was that Dragonfly 44 is embedded within an immense, crushing sphere of dark matter, a halo with a mass rivaling that of our entire Milky Way galaxy. This discovery turned galaxy formation theory on its head. We have a simple, intuitive model for how galaxies grow. Vast halos of invisible dark matter form first, their gravity drawing in ordinary gas. That gas cools, condenses, and eventually ignites into stars. The more massive the dark matter halo, the more gas it gathers and the more stars it should produce. Dragonfly 44 and other ultra-diffuse galaxies like it are spectacular failures of this process. They possess the dark matter foundation for a galactic metropolis, but they built only a tiny, scattered village of stars. How does a galaxy fail so completely at the one job it is supposed to do? The leading theory points to an early and dramatic quenching. Imagine the infant Dragonfly 44 beginning its life within the crowded, violent environment of the Coma cluster. As it fell into the cluster's dense core for the first time, it would have experienced a phenomenon known as ram pressure stripping. The space between galaxies in a cluster is not empty, it is filled with a thin, super-hot plasma. Moving at high speed through this plasma is like driving a convertible through a torrential downpour. The interstellar gas inside the young galaxy, the vital fuel for future stars, could have been violently ripped away by this intergalactic wind. Starved of fuel, the galaxy's star formation would have been strangled in its infancy, leaving behind a dark matter skeleton with only the stars it had already managed to create. Another possibility is that the gas it collected was simply too hot to cool down and collapse efficiently, perhaps due to a lack of the heavy elements that help radiation escape. Or more radically, the dark matter itself in these halos might have properties that somehow suppress the normal condensation of gas. These ghostly galaxies are more than just cosmic curiosities. They are critical stress tests for our entire understanding of galaxy evolution. They force us to ask whether our standard story is too simple, and if the path from dark matter to starlight can be severed in ways we are only beginning to imagine. Our own galactic home harbors a pair of colossal ghosts, emanating from the very heart of the Milky Way, stretching for 50,000 light-years above and below the galactic plane, are the Fermi bubbles. These are not made of stars or dust, but are vast twin lobes of superheated gas, glowing faintly in high-energy gamma rays, discovered only in 2010 by the Fermi Gamma Ray Space Telescope. Picture two titanic, hourglass-shaped balloons, each one reaching halfway to our galaxy's nearest neighbor, inflated from the central black hole we call Sagittarius, a star. Their sheer scale is humbling, a reminder that the quiet monster at our galaxy's core has not always been so dormant. The leading theory for their creation is a cataclysmic eruption from Sagittarius, a star itself, a violent feeding frenzy that occurred sometime in the past. As enormous amounts of matter spiraled into the black hole, not all of it crossed the event horizon. Instead, a fraction of that doomed material was channeled into two opposing, relativistic jets, punching through the galactic medium and inflating these gigantic cavities. The energy required for such a feat is staggering, equivalent to the simultaneous explosion of millions of supernovae. Yet, pinning down exactly when this happened is a detective story with frustratingly few clues. The bubbles are too diffuse and hot to hold clear chemical signatures of their age. Some estimates, based on the motion of gas at their edges, suggest the eruption could have occurred as recently as 2 or 3 million years ago, a mere blink in cosmic time when early human ancestors were already walking the Earth. Others propose a much older event, perhaps tens of millions of years in the past. This uncertainty leaves room for intriguing alternatives. Could the bubbles be the accumulated product of many smaller outbursts, or even the result of a period of intense star formation and subsequent supernova in the crowded galactic center, a collective wind rather than a single black hole sneeze? Regardless of their precise origin, the Fermi bubbles are a monumental fossil. They are a permanent scar, an echo of a time when our galactic center was a place of unimaginable violence, proving that even a quiet neighborhood like ours has a dramatic and explosive history written across the sky in invisible light. While titanic bubbles rise from our galaxy's core, another cosmic visitor is falling toward us from the void. Racing through the halo of the Milky Way at nearly 200 miles per second is a colossal, solitary cloud of hydrogen gas known as the Smith Cloud. Discovered in the 1960s by astronomy student Gail Smith, this structure is not a distant nebula. It is a massive, fast-moving projectile on a direct collision course with our galaxy's disk. Its shape is startlingly familiar, a vast comet-like plume with a bright, dense head and a long, trailing tail, as if the galaxy itself is breathing in a ghostly stream of primordial fuel. The scale is almost beyond comprehension. This cloud is approximately 11,000 light-years long and 2,500 light-years wide, containing enough hydrogen gas to forge over 2 million stars the size of our Sun. It is a river of creation, and it is about to pour itself into the galactic plane. The central mystery of the Smith Cloud is its origin, a question that splits into two equally dramatic possibilities. The first is that this cloud is the shredded remnant of a dwarf galaxy that ventured too close to the Milky Way's immense gravity. In this scenario, our galaxy's tidal forces stretched and tore the smaller galaxy apart, stripping away its stars and dark matter, leaving behind this pure stream of gas as a cosmic trophy. The second possibility turns the narrative inward, suggesting the cloud is a fountain of material violently ejected from our own galaxy. Perhaps it was blasted out from the tumultuous galactic center millions of years ago by the combined energy of supernova or black hole activity, and now, after a long arc through the halo, it is falling back home in a grand cyclical return. Recent observations have tilted the scales toward the extragalactic origin story. Measurements of the cloud's chemical composition reveal it is rich in sulfur, a signature that matches the outer regions of a dwarf galaxy, not the more metal-rich interior of the Milky Way's disk. It appears we are witnessing the ongoing cannibalization of a smaller neighbor, a process as old as galaxies themselves. The impact is inevitable. In approximately 30 million years, this immense hydrogen cloud will slam into the spiral arm of our galaxy, somewhere in the constellation Orion. The collision will be a spectacle of pure physics, not fire. The cloud will compress the existing gas in the galactic disk, triggering shock waves that ripple through the interstellar medium. These immense pressures will become the nurseries for a new generation of stars, igniting a brilliant burst of stellar birth across a region of space hundreds of light-years wide. The Smith Cloud offers us a rare and precious opportunity, a live preview of the galactic growth process in action. We are not just looking at a distant cloud, we are watching the future construction site of star clusters, watching as the raw material for solar systems and perhaps new worlds is delivered, reminding us that even our seemingly stable galaxy is a dynamic, evolving entity, still gathering its building blocks from the cosmic deep. That river of hydrogen gas is not our galaxy's only trophy from a cosmic encounter. Arcing across the southern celestial hemisphere, a pale, gossamer ribbon of gas stretches for over 600,000 light-years, nearly half the distance to our nearest galactic neighbor. This is the Magellanic Stream, a colossal filament torn from two of the Milky Way's most famous satellite galaxies, the Large and Small Magellanic Clouds. For decades, this stream was seen as a simple, tragic tale, the result of our galaxy's immense gravity slowly shredding its smaller companions as they orbit us. The story seemed straightforward, a tale of galactic tides pulling gas away, leaving a trail of debris in their wake. But the stream held a secret in its chemical makeup, a puzzle that refused to fit the simple narrative. When astronomers analyzed its composition, they found it contained surprisingly little oxygen, sulfur, and other heavy elements forged in stellar furnaces. This was odd because the Magellanic Clouds themselves are fairly rich in these elements. If the stream was simply stripped gas from the clouds, its chemistry should match theirs. This discrepancy suggested the stream's origins were more complex, perhaps involving gas pulled not just from the clouds themselves, but from a much larger primordial reservoir surrounding them. The breakthrough came with a revelation that rewrote the entire model. Observations from the Hubble Space Telescope revealed the Magellanic Clouds are not sailing through empty space. They are enveloped within a vast, diffuse corona of superhot gas. This corona is a shroud of plasma, 1,000,000 degrees Celsius, extending for hundreds of thousands of light years around the dwarf galaxies. Think of it as a protective, gaseous atmosphere on a galactic scale. This discovery changed everything. The prevailing theory now suggests that as the Magellanic Clouds orbit the Milky Way, it is not just their visible gas that is being stripped, but this immense hot corona. The Milky Way's own galactic corona, an even larger halo of hot gas, acts like a powerful headwind. As the clouds plow through this wind, their protective corona is compressed and stripped away, much like the outer layers of a comet are blown off by the solar wind. This stripped hot gas then trails behind the clouds, eventually cooling and mixing to form the cooler, denser hydrogen we see as the Magellanic Stream. This elegant solution explains the chemical puzzle. The hot corona gas would have had less time to be enriched with heavy elements from stellar explosions, matching the stream's observed purity. The Magellanic Stream is no longer seen as a simple tidal tail, but as the cooling wake of a galactic atmosphere, a sign of a dynamic, layered interaction happening on a scale we are only beginning to map. It shows us that galaxies do not interact as mere islands of stars, but as complex systems cloaked in their own weather, their fates written in the flow of invisible, superheated winds. This galactic weather is a prelude to a far grander atmospheric event, one that will reshape our entire night sky. Our Milky Way is not an island destined for solitude. It is on an inescapable collision course with its nearest giant neighbor, the Andromeda Galaxy. Right now, Andromeda is a faint, fuzzy smudge in the constellation named for the mythical princess, but it is a princess with a gravitational destiny. Hurtling toward us at 250,000 miles per hour, this immense spiral is destined to meet our own galaxy in a slow, cosmic dance that will culminate in a merger approximately 4 to 5 billion years from now. The certainty of this event, confirmed by precise Hubble Space Telescope measurements of Andromeda's motion, fundamentally shatters any lingering notion of galaxies as static, unchanging islands. They are dynamic actors in a gravitational ballet, their fates intertwined across the vast emptiness. The word collision conjures images of catastrophic stellar fireworks, but the reality is far stranger and more serene. The spaces between stars within a galaxy are so incomprehensibly vast that when the two galactic disks begin to pass through each other, actual stellar collisions will be extraordinarily rare. It will be less like a head-on car crash and more like two immense swarms of bees flying through one another, with the individual bees, the stars, almost never touching. What will collide violently is the diffuse gas and dust that fills the space between those stars. This interstellar material will be compressed, shocked, and ignited, triggering a brilliant wave of new star formation that will light up both galaxies from within. For billions of years, the gravitational tug-of-war will stretch and distort the majestic spiral arms of both Milky Way and Andromeda, pulling out long, luminous tidal tails of stars into the darkness. The two galactic cores, each harboring a supermassive black hole, will begin a slow, spiraling orbit, eventually merging into a single, even more massive black hole at the heart of the new creation. The final product of this multi-billion-year merger will likely be a giant elliptical galaxy, a featureless, football-shaped swarm of ancient stars. Astronomers have playfully dubbed this future entity Milkdromeda or Milkomeda. From this new galactic center, any future inhabitants would gaze upon a night sky devoid of a majestic spiral band. a sky populated instead by the blended, ancient stars of two former galaxies, along with the surviving, reshuffled satellite galaxies from both. This inevitable future is not a prediction of doom, but a revelation of cosmic rhythm. It illustrates that the universe is not a frozen snapshot, but an ongoing story of construction and transformation, where even the mightiest structures are temporary arrangements in an endless gravitational dance. That galactic merger is a single thread in a tapestry of staggering complexity. If we could step back far beyond Milkdromda, beyond Laniakea, and view the cosmos from a godlike perspective, we would see its true architecture. The universe is not a random scattering of galaxies, it is a web. This is the cosmic web, the single largest structure in existence, a vast, interconnected network of luminous filaments and dense nodes stretching across the observable universe. Picture the branching pattern of neurons in a brain, the delicate veins in a leaf, or the frothy bubbles in a sink of soapy water. This is the grand design of our reality, a blueprint written by gravity and dark matter over 13.8 billion years. The story of the web begins with the faintest whispers from the Big Bang itself. In that first searing flash, tiny quantum fluctuations, random ripples in the density of the primordial soup, were imprinted on the fabric of space-time. These ripples were the seeds of everything to come. As the universe expanded and cooled, gravity went to work. The slightly denser patches, dominated by the mysterious, invisible substance we call dark matter, began to pull in more matter. Think of dark matter as the unseen skeleton, the scaffolding of the cosmos. It does not shine, absorb, or reflect light, but its gravitational pull is irresistible. Over billions of years, this dark matter skeleton grew. The densest seeds collapsed into immense halos which became the nodes of the web, the future homes of galaxy clusters. The regions between them stretched and emptied, becoming the vast cosmic voids, and the material in between, the gas and dark matter that was neither in a dense node nor a deep void, was drawn into long, winding rivers and sheets, the filaments of the cosmic web. It is along these dark matter filaments that visible matter, the ordinary gas made of protons and neutrons, flows. This gas cools, condenses, and ignites into the galaxies we see, which themselves line the filaments like glittering dew on a spider's silk. For decades, this web was a theoretical prediction, a beautiful model born from supercomputer simulations. Mapping it directly was a monumental challenge because the filaments themselves are so faint, composed mostly of that elusive dark matter and extremely diffuse hot gas. But astronomers are now pulling back the curtain. New generations of telescopes, like the Very Large Telescope in Chile and future observatories, are using a clever trick. They look for the faint glow of hydrogen gas within the filaments, illuminated by the intense ultraviolet light from distant quasars, the brilliant cores of ancient galaxies. It is like using a distant spotlight to illuminate the fog in a valley. These observations are not just confirming the web exists, they are testing the very story of cosmic evolution. By measuring how much gas is in the filaments, its temperature, and how it is distributed, we can check if our simulations of the universe's growth from those first tiny ripples to the majestic web we see today are correct. Every new map is a test of our entire cosmological model, from the nature of dark matter and dark energy to the physics of the Big Bang itself. The cosmic web is the ultimate expression of structure in our universe, the final, beautiful pattern that emerges from chaos, and we are just now learning to see its full, luminous form. The cosmic web is the universe's final blueprint, but to understand how it was built, we had to look back to its very foundations. In 2003, the Hubble Space Telescope aimed its gaze at a single, seemingly empty patch of sky near the constellation Fornax, a region no larger than a grain of sand held at arm's length. For over 11 days, it collected every faint photon of light it could, peering deeper into space and time than ever before. The result was the Hubble Ultra Deep Field, an image that is not a structure in itself, but a profound window into the universe's youth, a core sample drilled into the cosmos. That tiny, dark speck of sky was suddenly filled with a breathtaking tapestry of nearly 10,000 galaxies, each a smudge of light that had been traveling for over 13 billion years to reach us. We were not looking at grand spirals or majestic ellipticals, but at the infant building blocks of the cosmic web, galaxies in their chaotic, formative years. The sheer number of them was the first great surprise. The early universe, it seemed, was far more crowded and industrious than many models had predicted. These were not just simple, proto-galactic blobs of gas either. Many appeared more structured and evolved than theories of the time allowed for. Astronomers saw disk-like shapes, clumps of early star formation, and hints of mergers already underway, all when the universe was less than 1 billion years old. This presented a clear and elegant challenge. How did gravity assemble such complex, star-forming structures so quickly after the Big Bang? The pristine image forced a revision in our timelines for cosmic dawn, suggesting that the first stars and galaxies ignited earlier and grew faster than our most careful simulations had shown. The Hubble Ultra Deep Field transformed a blank piece of sky into the most important history book ever written. Its every faint smudge a chapter in the story of how nothing became everything. It proved that the seeds of the great walls and filaments were sown in a frantic, brilliant epoch, a period of construction whose speed and efficiency we are still striving to fully explain. These deep field images show us the universe's first blueprints, but sometimes gravity itself becomes a lens, warping our view into impossible shapes. One of the most beautiful and useful illusions in all of astronomy is the Einstein ring, a perfect circle of light hanging in the void. This is not a physical structure like a wall or a filament, but a cosmic mirage, a trick of gravity so precise it feels like art. It occurs when a massive object, like a galaxy cluster, aligns almost perfectly between us and a distant, luminous source, like another galaxy. According to Einstein's theory of general relativity, mass warps the fabric of space-time. Light traveling along this curved geometry bends around the massive foreground object. When the alignment is flawless, the light from the background source is smeared and stretched into a complete circle around the intervening cluster, a halo of distorted reality. A stunning example is an object nicknamed the Molten Ring, found in the constellation of Fornax. Through the Hubble Space Telescope, it appears as a luminous, golden arc, as if a galaxy has been dipped in liquid light and stretched around a central point. The effect is not just beautiful, it is a powerful tool. These gravitational lenses act as natural telescopes, magnifying the light from galaxies so distant and faint they would otherwise be utterly invisible to our instruments. They allow us to see some of the earliest galaxies ever formed, peering deeper into the cosmic past than any human-made telescope could on its own. But the true power of Einstein rings goes beyond mere magnification. They allow us to map the invisible. The degree and shape of the distortion in the ring is a direct measure of the total mass of the foreground cluster causing the lensing. By carefully analyzing the ring's perfect curve, astronomers can calculate how much mass is there and, more importantly, where it is distributed. This has provided some of the most compelling and direct evidence for dark matter. We can see that the visible galaxies in the cluster do not contain nearly enough mass to create the observed bending of light. The ring tells us that immense halos of dark matter must be present, cradling the cluster, their gravity sculpting the light into these ethereal shapes. In this way, an illusion of gravity becomes our sharpest tool for seeing the unseen, transforming a beautiful cosmic coincidence into a precise scale for weighing the universe's deepest secret. Einstein rings reveal the universe's hidden mass through beautiful distortion, but sometimes gravity's power is expressed not in bending light, but in a blast of pure, unadulterated violence. In the constellation of Ophiuchus, the serpent-bearer, a galaxy cluster became the stage for the largest explosion in the universe since the Big Bang itself. This is the Ophiuchus supercluster eruption, a cataclysm of such staggering scale it makes every supernova ever recorded look like a tiny firecracker. The evidence for this ancient catastrophe is not a brilliant flash of light, but a ghostly cavity, a gigantic hole carved into the super-hot plasma that fills the space between the cluster's galaxies. This cavity is an immense spherical void spanning over 1.5 million light-years from edge to edge. To visualize its size, you could line up 15 Milky Way galaxies in a row and they would still not stretch across it. The cavity was discovered not by optical telescopes, but by instruments that see the universe in X-rays, the signature of gas heated to millions of degrees. The Chandra X-ray Observatory and other telescopes mapped the cluster's hot plasma and found a bizarre, sharply curved edge like the rim of a colossal bubble. Something had punched a hole in this seething, intergalactic atmosphere, pushing the multimillion-degree gas aside and leaving a cooler, quieter emptiness in its wake. The culprit is a supermassive black hole at the core of a galaxy in the cluster's center. This is the standard story of active galactic nuclei, where black hole jets inflate bubbles in their surroundings. But the Ophiuchus eruption is the ultimate extreme, a record-shattering outlier. The energy required to carve this single cavity is almost beyond comprehension, estimated to be around 5 times 10 to the 54 joules. That is hundreds of times more energy than a typical, already violent cluster eruption, and it is 5 times greater than the previous record holder, a blast in the MS-073 5.6 plus 7421 cluster. To put that number in human terms, this single event released more energy than the Sun will produce over its entire 10 billion-year lifetime, multiplied by several trillion. It is the equivalent of detonating 20 billion megaton nuclear bombs simultaneously. This immediately forces a critical question. How can a single black hole, even a supermassive one, unleash such a titanic amount of energy? The leading theory suggests this was not a single, brief outburst, but a sustained eruption lasting for perhaps 100 million years. Imagine a volcano erupting continuously for 100 million years, its lava flows reshaping an entire continent. The black hole's jet, a focused beam of plasma moving at nearly the speed of light, must have remained stable and incredibly powerful for an epoch, relentlessly boring into the cluster's atmosphere. The sheer stability of such a jet over that timescale is a profound mystery in itself. Another possibility is that we are seeing the result of a particularly efficient feeding event, where the black hole consumed an unprecedented amount of material, perhaps an entire galaxy's worth of gas, converting it into jet energy with freakish efficiency. The Ophiuchus cavity pushes our models of black hole feedback to their absolute breaking point. We thought we understood the maximum power these cosmic engines could produce, but this fossilized explosion tells us we have likely underestimated their potential for violence by orders of magnitude. It stands as a permanent monument to an era of unimaginable fury, proving that the quiet black holes we see today are capable sleeping giants whose past roars once shook the fabric of the cosmos on the grandest possible scale. Amidst the universe's cataclysms and collisions, one galaxy stands apart as a monument to quiet, persistent growth. This is UGC 2885, a spiral galaxy of such immense and serene scale it has earned the nickname the Godzilla Galaxy. Located 232 million light-years away in the constellation Perseus, it is a cosmic leviathan, a spiral disk stretching over 463,000 light-years from edge to edge, more than 2.5 times wider than our own Milky Way. It contains perhaps 10 times as many stars, yet for all its staggering size, this is a gentle giant. Its spiral arms are loose and relaxed, not tightly wound or distorted by recent violence. It drifts in a profound and lonely region of space, a true cosmic island with no significant galactic neighbors for millions of light years in any direction. This isolation is the first clue to its mystery. In a cosmos where we believe the largest galaxies are built through a relentless series of violent mergers, the Godzilla galaxy presents a paradox. There is no evidence of a tumultuous past, no tidal tales of stolen stars, no disrupted core from a recent collision. Its peaceful existence challenges the dominant narrative that to become a giant, a galaxy must be a cannibal. So how did it grow so immense? The leading theory is a story of patience, not power. Astronomers suspect UGC 2885 has spent its entire multi-billion-year life in a state of serene, steady accretion. Instead of violently consuming other galaxies, it may have been slowly sipping on the thin, primordial gas that permeates intergalactic space. Imagine a vast, cosmic sponge floating in a mist, gradually absorbing droplets over eons until it becomes impossibly heavy. This process, known as cold gas accretion, would allow for the continuous, quiet formation of new stars across its vast disk, building its stellar population gradually and peacefully. Its supermassive black hole, too, appears quiet and underfed, further supporting the idea of a calm evolutionary history. This galaxy forces us to consider an alternative pathway to greatness. Perhaps in the quietest corners of the universe, where the gravitational tides of neighbors never stir the waters, a galaxy can simply grow into its enormity through the slow, steady accumulation of the universe's raw material. The Godzilla galaxy is a testament to the power of solitude, proving that cosmic majesty can be born not from chaos, but from an almost meditative calm, a billion-year sigh that built one of the largest and most peaceful spirals we have ever seen. That gentle giant, the Godzilla galaxy, shows us the power of solitude, but our own cosmic neighborhood holds a puzzle of a different kind. Just 3 million light-years away, a familiar spiral galaxy is hiding a secret in its faint outer glow. This is M33, the Triangulum Galaxy, the third largest member of our local group after Andromeda and the Milky Way. For years, it was considered a classic, unbarred spiral, a smaller and quieter cousin to its massive neighbors. But recent, painstaking observations have peeled back its outer layers to reveal something startling. Surrounding its bright spiral disk is an immense, structured halo of ancient stars, a halo far more massive and complex than any model predicted for a galaxy of its size and type. This is not a faint, diffuse cloud, but a halo with clear substructure, streams and clumps of stars that tell a story of a turbulent past. For a galaxy like Triangulum, which is only about 1/10 the mass of the Milky Way, such a prominent and intricate halo should not exist under standard formation theories. These models suggest that large, structured halos are built primarily through the cannibalization of smaller dwarf galaxies over billions of years. A galaxy as relatively light as Triangulum should have had a quieter history with fewer dramatic mergers, resulting in a much fainter and smoother stellar halo. The fact that its halo is so rich and textured forces a dramatic reinterpretation of its life story. The most compelling explanation points directly to our two giant neighbors. The intricate streams and overdensities in Triangulum's halo are likely the gravitational scars of a close encounter, or even a series of encounters with the Andromeda galaxy. Computer simulations show that as a smaller spiral like Triangulum swings past a behemoth like Andromeda, the larger galaxy's immense gravity can violently strip stars from the smaller one's outer regions, stretching them into vast tidal streams that eventually settle into a structured halo. It is a cosmic fingerprint, evidence that Triangulum has not been sailing in peaceful isolation, but has been dancing a dangerous gravitational tango with Andromeda for eons. This discovery does more than rewrite the biography of a single galaxy. It challenges our fundamental understanding of how spiral galaxies grow their outer envelopes. It suggests that even for galaxies we consider modest, the process of halo formation can be dominated by a few major, disruptive events rather than the slow accumulation of many tiny mergers. Triangulum's halo is a living archive, a record of past violence written in the trajectories of billions of ancient stars. As we look toward the inevitable future merger of Andromeda and the Milky Way, Triangulum's story offers a poignant preview. This smaller spiral is caught in the gravitational wake of giants, its shape and destiny already being sculpted by forces far greater than itself. Its unusually massive halo is a testament to the interconnectedness of our local group, a reminder that in the cosmos, no galaxy is an island, and the faintest glow can hold the deepest history. From the ghostly halos of our nearest neighbors to the echoes of the largest explosion since time began, these 25 cosmic marvels are more than just a catalogue of the universe's greatest hits. Each one is a clue, a cosmic outlier scribbled in the margins of our textbooks. The immense walls and arcs defy our models of cosmic smoothness. The inexplicable flows and cold spots whisper of influences from beyond our horizon. Galaxies that are too big, too quiet, or too perfectly formed challenge every story we tell about how islands of stars are born and evolve. Every single structure we have explored exists at the very edge of what our physics says is possible, each one a beautiful, glaring exception that forces scientists to question, to refine, and sometimes to completely overhaul our fundamental understanding of reality. They are not errors in the data, they are the data, screaming that the universe is far stranger, more creative, and more magnificent than our best theories ever predicted. This is not the end of the story, but a new beginning. The next generation of eyes on the cosmos is already opening. The James Webb Space Telescope peers into the cosmic dawn, searching for the infant seeds of these colossal structures. The Vera Rubin Observatory will soon begin a relentless, decade-long scan of the entire sky, uncovering millions of new anomalies we cannot yet imagine. With every new map of the dark and the distant, we are guaranteed to find structures that bewilder us all over again, pushing the boundaries of the possible even further. So tell us, as we stand on this precipice of new discovery, which of these cosmic mysteries captured your imagination the most? Was it the perfect ring of Hoag's object, the terrifying pull of the dark flow, or the serene scale of the Godzilla galaxy? Share your thoughts below and let's keep looking up together.